We will now continue with our discussion on energy by discussing an all-important concept, the conservation of energy. What does conservation of energy means? Now, in Unit 1, we talked about the conservation of momentum. I hope you remember that concept. Well, we said in a closed system, the total momentum of the system remain unchanged. Momentum can be transferred from one object to the other, but the total momentum remain unchanged. In the same way, universe is a hub of energy. In fact, what is this universe? I told you about this some other time. The universe is a great big pot of energy. And energy can be transferred from one form to another. You and I are some versions of that energy, some blimp of energy in that big pot of energy in the universe. The total energy is a constant. Nothing gets added to it, nothing gets removed from it. But energy continuously changes from one form to another. Right? That is the essence of conservation of energy. Now, in the classroom situation, let me take a small example to talk about it. Now, as a ball is taken up to the top of a stairs, suppose you have a ball and you take it up to the top of a stairs, what happens? You are doing work on the ball to increase its potential energy. Is that right? Its potential energy increases because you are doing work on it to raise it. So here I have at the bottom of the stairs, its potential energy is 0. You keep climbing with it, means you are raising it. Now suppose, I'm just giving you a figure without calculation. Suppose at the top of the stairs, its potential energy is 50 joules. So you did 50 joules of work to reach the top of the stairs. Now let the potential energy at the top is U equal to 50 joules. Alright? The potential energy there is 50 joules. Since it has no speed, now you took it there and kept it at the top of the stairs. It has no kinetic energy, it has no speed. Now this is not sped, but speed. Now since it has no speed at this position, its kinetic energy K is 0. So what is the total energy at that position? The total energy of the ball at the top of the stairs is 50 plus 0, that is potential energy plus kinetic energy equal to 50 joules. Okay, now what happens if the ball is now rolled down the ramp? If you now allow this ball to roll down and come here, what happens? Now this is where energy change occurs. You can see the potential energy is going to be converted to kinetic energy. All the potential energy it has at the top becomes kinetic energy at the bottom. You see, once it reaches the bottom, it comes with a good speed. Where did it get the speed from? Well, the speed it acquired because it had an original potential energy. Now, kinetic energy at the bottom, all that potential energy, all this 50 joules now becomes kinetic energy. So its kinetic energy is 50 joules, and that will be 1/2 mv squared. Now, so at the bottom of the stairs, the kinetic energy is 50 joules. What is the potential energy when it comes back to the bottom? At the ground level, the potential energy is 0. So what is the total energy at the bottom of the stairs? The total energy is potential energy plus kinetic energy, that is again 50 joules. Now that means no matter where this ball is, that total energy 50 joules is going to be a constant. But the potential energy can get transferred to kinetic energy, kinetic energy can get transferred to potential energy, but the total energy will not change. As the ball rolls down, you can see if you keep the ball at a position like this, when it comes here, it will have both potential energy and kinetic energy. And if you add the potential energy and the kinetic energy, that will also be 50 joules. The conservation of energy, the conversion of energy from one form to another happens all the time in the universe. In fact, life is possible on the earth because energy from the sun is converted to many other forms. Now, where do we get the electrical energy from? The origin of the electrical energy that we use here is the energy from the sun. Right? Yes, that's right. The source of all the energy on the earth is the energy from the sun. Now, the total energy in the universe always remain a constant. It never gets taken away, it never gets added to it. The total energy always remains a constant. And this principle is called the principle of conservation of energy. That's an all-important law in physics. Now, the law goes like this: in a closed system, energy gets converted from one form to another, but the total energy in the system always remains a constant. Life on Earth is made possible because of energy conversions and energy flow. The cycle of work and energy is the best way to understand the energy cycle. Alright, we'll talk about the cycle of work and energy. When you do work on something, you give it energy. Is that right? Now, we see this all the time. Have you seen somebody splitting wood? Take the axe and raise it to a height. Give the axe potential energy and bring it down to the wood. But the potential energy becomes kinetic energy. The work you do. You see, the food we eat gives us energy. And the energy we have, we can do work with. And when we do work, we can give energy to other objects. And those objects can then do work. Look at that. The conversion of energy into work and work into energy is a continuous process that goes on in this universe. And that's a beautiful process. And that is what keeps us all going. Right? Alright. I hope this is an interesting concept for you to think about. Now, in turn, objects that have energy will do work on something else, and the energy cycle will continue. Alright, let's do a lab to test the conservation of energy. What we're going to do is, we're going to give an object a potential energy, and then we are going to allow it to drop so that it gains kinetic energy, and we're going to calculate the energy at both places and see if the total energy remains the same. Alright? For that, you remember your potential energy. How do we calculate potential energy? Potential energy is calculated as U equal to mgh. So make a note of this, because I'm going to erase this. Take a note of this, and kinetic energy is 1/2 mv squared. Alright, so keep track of this. We are going to calculate the potential energy and kinetic energy of an object at different places to prove or to test the conservation of energy principle. Alright, let's do that. Give me a second to set up the lab, and I'll be with you in a minute. What we're going to do is to use a pendulum. Now, what is a pendulum? Do you know what a pendulum is? Now, this is a pendulum that I can set into oscillation to move back and forth. Now, when the pendulum oscillates, can you see the pendulum oscillating? Now you raise it to a height, giving it potential energy, and now let me keep it like this. You raise the pendulum to a height, giving it potential energy, and when you let it go, it's going to fall, gaining kinetic energy. Now what happens in this case is potential energy at this point becomes kinetic energy at the bottom, and when it reaches here, because it has a speed, that kinetic energy is going to give potential energy. Now we have what the oscillation here. Now here, potential energy, kinetic energy, potential energy. Now the energy gets converted continuously. Alright, now this is a good example of conservation of energy. The potential energy here becomes kinetic energy. You can see if I keep my hand, I get hit by that kinetic energy. Now if my hand is not there, because of the speed it acquires, it goes and climbs to the other extreme. So energy gets converted to potential, to kinetic, to potential, to kinetic, and the energy conversion happens continuously. And now I have an animation here. Watch the setup of a pendulum like this. Now watch how the pendulum oscillates. The pendulum oscillates back and forth. Is that right? Right. Now the pendulum climbs to a height. It has potential energy. What's the potential energy? Its potential energy is now gradually gets converted to kinetic energy. When it comes here, all the energy is kinetic, and it climbs to there, gaining potential energy. You can actually measure. Now here, all the energy is potential, and now potential energy is going to, yes, decrease, kinetic energy increases. All the energy is kinetic here. I want you to watch this very carefully. Look at how the conservation of energy works. Now, potential energy and kinetic energy is continuously changed from one form to the other. So its potential energy now is U equal to mgh at the height h. If it is at a height h, the potential energy is mgh. Here, all the energy is potential, that is equal to mgh. When you leave the bob, it falls to the lowest position. All the energy here is kinetic. Now what we are going to do, we're going to set up the pendulum and do this experiment. We will measure its speed using a photo gauge at the lowest point. Now let me tell you how we're going to measure the speed. Now we are going to allow, you have seen the photo gauge that we have been using. We're going to allow the pendulum bob, we're going to allow the pendulum bob to go through a photo gauge and measure the time taken for it to go through. Then we can calculate the speed of this by dividing the diameter of the ball by the time taken. The time will be measured by the clock. So in the experiment, you will be measuring the speed of this. Now how do you calculate the speed? I want you to make a note of that. Speed is calculated like this. So we will calculate speed equal to diameter of the ball divided by the time. I'm going to give you the diameter of the ball. The diameter of the ball is 0.04 meter, and the time you will be measuring. And we will use this formula. Speed of the ball is the diameter of the ball divided by the time taken by the ball to go through the photo gate. I'll set it up in a minute. And that will give me the diameter is 0.04 meter and the time we will measure using the photo gate. And that way we will calculate the speed of the ball, and we will calculate the kinetic energy. Alright, I'll be setting up that. Alright, watch the experimental setup. I want you to watch it carefully and see how to fill in various quantities. Now, first of all, I'm going to keep the ball of the pendulum at a height h, which I'm going to measure and give it to you. In other words, when I move it from here, what is the height I'm going to raise it? I will give you that height over there, and you will then calculate its potential energy using potential energy equal to mgh. That means we need to start with the mass of the ball. Now I started the mass, I measured the mass of the ball, and I'm going to write it down here. Now you got your worksheet, so write down the mass of the ball in your worksheet. I'm going to write it there. It is 0.3 kilogram. The mass of the ball is 0.3 kilogram, and the diameter of the bulb is 0.04 meter. Those are the two values you need to know. The mass of the bulb is 0.3 kilogram, its diameter is 0.4 meter, and we will measure the speed. What we're going to do is we're going to measure the speed as it goes through the photo gate. The time taken will be registered here, and the diameter, you see, that's the distance during that time. So once you know the diameter, the speed of the bulb will be that diameter divided by the time. In other words, it will be 0.04 divided by the time we measure. I'm going to do one run and show it to you and calculate the potential energy and the kinetic energy. Now I'm going to do the first run and show you how to deal with the data. Alright? Now I'm going to start by pulling this bulb up. You know, this is the gate. I just moved it a little to make it a little more accurate. So that's the gate there. I'm going to move the bulb up by 10 centimeter. 10 centimeter is 0.1 meter. So the height is going to be 0.1 meter, and we will calculate the potential energy, and I will fill up my data like this. H is 0.1 meter, so the potential energy, I'm going to calculate it below the table. Potential energy U equal to mgh. Now what is the mass of the bulb? I give you the mass of the bulb as 0.3 kilogram, so that will be 0.3 times 9.8 times H is 0.1. Can you calculate that for me? 0.3 times 9.8 times 0.1 is 0.29 joules. So my potential energy is 0.29 joules. And now I'm going to measure the time. For that I need the diameter. I told you the diameter is 0.04 meter. Alright, I'm going to raise, first of all let me reset the clock. I'm going to raise the bulb to 10 centimeter. You can see I have raised the bulb now at just a height of 10 centimeter, and I'm going to leave it. Let's see what the clock reads. The clock reads 0.0281. Alright, I'm going to use that time. The time is 0.0281. Therefore, look at the way I'm going to calculate the velocity. V equal to the diameter of the ball divided by the time. That will be 0.04 meter divided by 0.028 second. Can you calculate that for me? 0.04 divided by 0.028 is 1.4. So the speed of the ball is 1.4 meter per second. So the ball had potential energy here. How much is the potential energy? 0.29. And when we left it, all that potential energy became kinetic energy at this position where I'm showing. And we measured the velocity at that position, and the velocity is 1.4 meter per second. Let's calculate the kinetic energy. Kinetic energy is 1/2 mv squared. So look where I'm going to calculate. Can you see that? I calculated the velocity here. I'm going to calculate the kinetic energy at the bottom. K equal to 1/2 mv squared. M is 0.3. V squared is 1.4 squared. And on the calculator, type in 1/2 as 0.5 times 0.3 times 1.4 squared is 0.29. Now, isn't that a good agreement? The kinetic energy is 0.29 joules. Now, what that means is all the potential energy at this height now got converted to kinetic energy. You see, look at the conservation of energy. All the potential energy at that height is converted to kinetic energy. Alright, what I'm going to do is I'm going to do 4 more trials. I will raise it to different heights. Now let me see how much is the maximum height I can actually go. Well, let's see. I'm going to make the height now 15 centimeter, in other words 0.15. Alright, I'm going to make the height 0.15, and I'm going to leave all these columns for you. Calculate the potential energy and now measure the time. I'm going to, let me reset the clock and let's measure the time when the height is now 15 centimeter, and you can see I have a ruler here to measure it. So the height is 15 centimeter. I'm going to leave it. What is the time? 0.0203. Alright, have you written it down? 0.0203 is the time. 0.0203. Okay, I want you to calculate the speed of the ball as it passes the gate, and calculate the kinetic energy, and see how the potential energy compares with the kinetic energy. Alright, I'm now going to take the height to 20 centimeter. Alright, let me reset the clock. I'm going to make the height 0.2 meter. So this is going to be 0.2 meter. Alright, I'm going to raise it to 20 centimeter. There it is, 20 centimeter. And the clock is reset. Alright, let's see. I'm going to leave it, measure the time. There we are. The time is 0.0197. .0197 is the time. Okay, well, the time now got changed because the pendulum bob has been going back and forth inside the gate. But our measured time is .0197, and I want you to calculate the speed of the bob and its kinetic energy. Okay, I'm going to now raise it to 0.25, 25 centimeter, 0.25 meter. Calculate the potential energy. So you must calculate the potential energy. And now let's measure the speed as it passes the gate. Alright, let's I'm going to raise it to 0.3. That will be, where will that be? That will be 0.25. 52. See if I can get it. There I have a 0.25. I'm going to leave it. Let's see. There. That's 0.1211. The energy was so much, it took away my pendulum. 0.1211. That was the time. Well, it was 0.1211. I hope you got to read that. That would be 0.0121. Not this time. This has been disturbed because it fell off. Alright. You want to try again? Let's try again. Alright. I want to bring my pendulum back and reset the clock. Okay. Make it there you are. Now the height is 25 centimeter. My clock is not reset. Alright, let's see how it's going to work. Well, this time I got 0.0073. Alright, let's take that one. 0.0073. I got two values. Alright, I want you to take the average of those two values. So one value is 0.021, the other value is 0.0073. Alright, so for this height, I got two time values because of the mess up. I want you to take the average of these two values. I hope you understand. I got two values there. Find the average of those two values as the time there. Alright, I'm going to try one more. That is 0.3. And let's see if I can do that. It's going to be pretty difficult, but we will try. Now I'm going to raise it to 0.3. There I'm at 0.3. Can you see where I am? I'm far out there. And let's see if we can get a measurement made. 0.3. And there we go. The time is 0.0035. 0.0035. That is the time. That would be 0.0035. That is when the height is 0.3 meter. Alright, we got all the measurements we need. So we have all the measurements. I have given the heights, calculate the potential energy for each height, and we have measured the time taken by the pendulum bob to pass through the photo gate, and knowing the diameter, divide the diameter by that time to obtain the speed and calculate the kinetic energy. And if the conservation of energy is true, the amount of potential energy must be very nearly equal to the kinetic energy. Well, we have experimental error all the time, is that right? But you can see my first trial was very good. So what do I want you to do? Complete this and complete your worksheet and email it to me. And that's what I want you to do, and that is a good lab. Alright, so complete the lab worksheet and email it to me. Alright, let's continue. We will now talk about the different forms of energy. I told you this world is brimming with energy. What are the different forms of energy that we are used to? Can you tell me some different forms of energy? We talked about two forms of energy already here, potential energy and kinetic energy. And these forms of energy is called mechanical energy. Now, when a flywheel rotates, it has mechanical energy. So this is the familiar form of energy that we associate with machines. When your car engine works, you can see a lot of things will be moving, and the motion energy, that is kind of mechanical energy. So potential energy and kinetic energy are both mechanical energy. Now, kinetic energy of a moving train, potential energy of a compressed spring or a stretched spring. You know that if you compress a spring or stretch a spring, it has potential energy because it is capable of doing work. And all these are examples of mechanical energy. Well, another most important type of energy is chemical energy. Chemical energy is the energy associated with chemical reactions. Whenever chemical reactions occur, either energy gets released or energy gets absorbed. Energy is released in one form of chemical reaction known as oxidation. You see, when hydrogen and oxygen combine to form water, a large amount of energy is given out. In fact, if you have large amounts of hydrogen, we can produce large quantities of energy very cheap. In fact, that is what we are now trying to do, produce cars that will run on hydrogen, right? Now, when substances burn, they combine with oxygen in the air, releasing energy. If you burn wood or coal, the process is the substance will combine with oxygen, and that chemical reaction will release energy. Now, energy is locked up in wood and coal and so on when you burn it. In other words, when the substance combines with oxygen, that locked up energy gets released. Now, don't think that we are producing energy. We are not producing energy. We are only converting energy from one form to another when you burn coal or wood. So burning wood can be represented, look at this, wood plus oxygen. Now, when wood combines with oxygen, what are the things that are produced? Carbon dioxide is produced. Anything when it burns, one byproduct is carbon dioxide, and water, that is harmless, and a lot of energy. This is the equation. We call it the chemical equation. Wood reacting with oxygen produces carbon dioxide, water, and energy. Large amount of energy. The locked up energy in wood gets released. And this process is called combustion. Any process where the internal locked up energy is released. You see, in your car, you pour fuel, gasoline into your car. Now, inside the engine, gasoline and air is mixed, and that mixture is burned. In fact, what happens inside your car is combustion. And as a result of combustion, what are the things that are formed? There are a lot of carbon dioxide, water, and a lot of energy. So it is the same kind of equation. So what is combustion? Combustion is when the substance combines with oxygen, releasing the locked up energy inside the substance. In photosynthesis, what is photosynthesis? Plants use up energy from the sun and water from the soil to manufacture their food. In fact, their food then becomes the plant material. Plants grow by manufacturing their food. Now they use energy from the sun, water from the soil, and carbon dioxide from the air. You see, a lot of carbon dioxide that is released into air as a result of combustion are used up by plants to manufacture their food, right? So that process is called photosynthesis. Photosynthesis. Plants use energy from the sun to rearrange carbon dioxide and water molecules to form plant materials. Plants grow by producing plant materials and oxygen. During that process, plants release a lot of oxygen. And that's the reason why planting trees and shrubs around your home is good for you. It produces a lot of oxygen. It consumes a lot of carbon dioxide and releases oxygen. So look at the equation there for photosynthesis. Energy plus carbon dioxide plus water. Plants use energy from the sun, carbon dioxide from the air, water from the soil, and it produces plant materials and oxygen. Alright, now this is nature's balance. We pollute the air, plants clean it up. So plant a lot more trees so that they can do a better job. Now this is part of the energy cycle in nature. Energy used in photosynthesis is released during combustion. You see, during photosynthesis, plants receive or absorb energy from the sun, and that energy is locked up in the plants. And when we burn plant materials or when we allow combustion to take place, that locked up energy is released. So this is the part of the energy cycle in nature. Chemical energy is a kind of potential energy. You see, any energy that can be released from locked up position is actually potential energy. Chemical energy is kind of potential energy that is stored and later released during the chemical action. Now plants use of carbon dioxide in the atmosphere. Look at that, carbon dioxide is absorbed and water is absorbed and sunlight is absorbed. It produces sugar. That is what becomes plant material, cellulose. So sugar and oxygen, which is released to the surroundings. And the reverse process occurs in animals. What do? We take in oxygen, and the respiration process that happens in our body, we manufacture, we take in food and oxygen, and the combustion inside our body produces carbon dioxide. You see, the reverse process happens in animals. The sugar molecules from the food we eat combines with oxygen that we breathe, producing energy. You see, how much energy do we have? We go around and do a lot of work every day. Where do we get all that energy from? That energy we get from combustion of the food that we eat with oxygen. You see? And the food we eat is broken down into sugar molecules. And these sugar molecules combine with oxygen, producing energy, carbon dioxide and water. So look at the equation. Sugar plus oxygen is carbon dioxide plus water plus energy. This is exactly opposite of what happens in plants. Now this process balances the amount of carbon dioxide in the atmosphere, but our activities have piled up so much carbon dioxide in the atmosphere that plants alone cannot clean it up. We need to have our own initiative to clean up the air, to make the planet green. So that movement is very important. I hope you take that seriously. Now think of some of the ways this balance is disrupted by human activity and the contribution that makes to global warming. Again, if you want to write a paper on it, I will treat it as an extra credit. Alright? So the amount of work, I want you to do as much as possible in this course. I'm not requiring you to do that, but if you want to do it, that will be an extra credit. So think of some of the ways this balance is disrupted by our actions and the contribution that makes to the global warming. Let's now talk about fossil fuels. What are fossil fuels? Fossils are things that are buried and kept away, hidden from us for a very long time. Substances that release energy due to combustion are called fuels. Any material that combines with oxygen in the process of combustion that releases energy is a fuel. Petroleum is a fuel. Wood is a fuel. Coal is fuel. And the food we eat is a fuel for us. Now, fossil fuels are formed from fossilized animals and plants that were dead and buried millions of years ago. Now, oil and coal are two major sources of fuel we have at present, and they are both produced from fossilized animals and plants. Let's talk briefly on coal. Now, coal, how is coal formed? Now, the energy in coal comes from the energy stored by plants that lived hundreds of millions of years ago when the earth was partly covered with swampy forest. Millions and millions of years ago, the earth was covered with swampy forest. Now, these swamps were buried and covered by layers of water and dirt as a result of millions and millions of years of change on the surface of the earth. Now, when you pile up mud and dirt on top of all these dead plants, the pressure increases and the temperature also increases. What happens as a result is those dead plants, remember there are millions and trillions of tons of those, are actually cooked underneath. And as a result of millions of years of this increased temperature and pressure, they get pressed and cooked and they get transformed into what we call today coal. So coal is a material that has transformed in years and years of subjected to this great pressure and temperature of plants that lived millions, hundreds of millions of years ago. And now you can see dirt and everything piled up and the pressure and temperature increased and this layer got pressed and compressed and cooked, became coal. There you got the coal. And now what you have on top of that, you got a big layer of the earth's surface. So in many places, if you want to get to that coal, you got to dig down and go into a mile, 2 mile or 3 mile down to the surface of the earth. And that is what a lot of our coal miners do these days. Look at the hard work they do. And sometimes they get killed because of the poor safety conditions in the mines. Now, United States produces 1/5 of the coal produced in the world. You see, producing coal is not a very easy task. Going down underground and getting this precious fuel out is a very tedious job, and we lose a lot of life in the process. Coal is used to generate more than half of all the electricity produced in the United States. Besides, electric utility companies, industries and businesses with their own power plants use coal to generate electricity. You can see it's used widely. Now, power plants burn coal to make steam. Actually, electricity is produced by turning a big coil of wire called a turbine inside a magnetic field. You need tremendous amount of energy to turn it. When you turn a turbine inside a magnetic field, it generates electricity. Now, let me show you a small demo. Now, I have a coil of wire over here. This is a coil of wire, and instead of rotating the coil of wire, I'm going to move a magnet. Now, this is a magnet I'm holding. Now, watch what happens to the meter. This is a meter that will detect electricity flowing in this wire. See what happens when I move the magnet. Tell me what is happening. Well, this process produces an electric current. So, in a electricity generating plant, great big coils like this are rotated inside a magnetic field, or great big magnets are rotated inside a coil, and that will generate electricity. And we need a lot of energy to do that. So what is happening is we use coal to boil water, and the steam that is generated is injected by very fine nozzles onto the turbine. The turbine will rotate. See, in order to rotate the turbine, you need energy, and the steam will supply that energy. And that is how electricity is produced. So the steam turns turbines which generate electricity. When coal is burned as fuel, it gives off carbon dioxide, which is the main greenhouse gas that is linked with global warming. Burning coal also produces other emissions such as sulfur, nitrogen dioxide, and mercury that can pollute air and water. So, we need energy. All of us need electricity. Is that right? That means we need to burn coal. But burning coal and producing electricity for us is going to throw away all these pollutants into air. That means we are making the environment unsafe for us. So one of the things that you need to learn as a result of that, we need to learn to conserve our energy consumption. If everybody in the United States cut down their consumption by 10%, which is not difficult. Do you know that our environment can be protected of thousands of millions of tons of carbon dioxide? Yes, it can be. So that's the reason why I told you in one of the labs earlier, think of some of the ways you can conserve and save energy. All right. Now, petroleum, another fossil fuel. Where does petroleum come from? Petroleum, like coal, is formed from the decayed remains of prehistoric marine animals and terrestrial plants. In fact, most of the petroleum that we get are from fossilized animals. Now, over many centuries, this organic matter mixed with mud is buried under thick sedimentary layers of materials subjected to great pressure and temperature, and is systematically being cooked and transformed into oil. The resulting high levels of heat and pressure caused the remains to change into what we now call crude oil. And you can see how expensive and how demanding, what demand that this have now. A barrel of crude oil is now selling for $85. Do you know that about 20 years ago it used to sell for $22? And now it is selling at $85. Look at the need for conservation. Alright, so petroleum is a hydrocarbon which gives out large amounts of energy when it undergoes combustion. When it combines with oxygen and is burned, when it undergoes combustion, it gives off a large amount of energy. All the locked up energy in it is released. And we use it to run our cars, to run our trains, to run our industries, you see. But in the process, it has also a lot of unwelcome byproducts which fouls up our environment. But burning oil releases carbon dioxide into the atmosphere, which is the prime contributor towards global warming. Oil reserves are not replenishable. Now, one day these oil reserves are going to run out. Where are we going to go for our energy then? Now, isn't it wise for us to start thinking about it now? I talked about hydrogen as a source of fuel, but we are not there yet. We are not ready to use hydrogen as a fuel yet in massive scale. We need to find alternative to fossil fuels. And one of the ways is, again I emphasize, you know, in this course, I will keep on telling you this, the need for conservation. You see, you learn to drive smaller cars. You go to Europe and other countries, you can see the cars are very small. You rarely find great big cars like American roads. In America, we are so used to luxury. You see, luxury is expensive. People will say, well, I can afford it. Well, yes, you can afford it, but somebody else cannot afford it, and the environment belongs to all of us. That means we have a collective responsibility to protect it. Is that right? Okay. Now, in order to sustain our civilization and cleaner environment, we need to conserve energy and look for alternative and renewable sources of energy. Well, we have been looking for it, we have been working on it, and we are gradually succeeding. Well, we might get there one day. Another kind of energy is the radiant energy. All the energy that we get from the sun is radiant energy. Well, the origin of all our energy source is the radiant energy from the sun. Radiation from the sun reaches in a wide spectrum of energy called electromagnetic spectrum. You see, electromagnetic waves or electromagnetic radiation is actually given off by objects at every temperature. This object will give off electromagnetic radiation. I am giving off electromagnetic radiation. But what's the difference between the electromagnetic radiation that I give off, this one gives off, and the sun gives off? They are really all the same type, and they differ in what is called wavelength and frequency. We'll talk about it. So, the energy waves are characterized by wavelength and frequency. Now, what is a wave? A wave has a crest and a trough. All right, let me try and draw that for you. Now, here I have a wave. This wave has wavelength. Now, look at another wave. A shorter wave, a still shorter wave, a still shorter wave. So, electromagnetic radiations consist of a large spectrum of waves Now, some of them are very long, kilometers long. The length of a wave is a crest and a trough together. So this is one full wave of a very long wave. This is one full wave of a short wave. So a wave has a wavelength. You see, this is one full wavelength for that wave. Now, the wave I am giving off, the radiation I am giving off is a very long wave. It's called infrared. And there are even longer waves, radio waves. You see, this object at the room temperature is actually giving off radio waves. Radio waves are very long, about a kilometer long, you see. And then infrared are heat rays. And as you come shorter, the visible light comes from the sun is still shorter. Then other radiations like X-rays, gamma rays, they are still shorter. So I want you to understand and make a note of this. The electromagnetic radiations that are emitted by objects. Objects at all temperatures emit electromagnetic radiations. And they consist of very long waves to very short waves. Now, depending on the wavelength, the properties of these radiations will differ. All right? Okay, let's continue now. So here we have one type of wave. This is the wavelength that we call lambda. That's the long wave. When the wave is very long, its frequency is small. The frequency means the number of waves produced per second. That's the frequency. When the waves are very long, only a few waves are produced a second. So a very long wave has very low frequency. Now, short waves, you see the wavelength is short. Short waves are very high frequency. Now, the energy of a wave depends on the frequency. If the frequency is low, the energy is low. The frequency is high, the energy is high. That's how the energy is determined of a... Now, high frequency waves carry more energy. Now here, I have a picture of all the electromagnetic radiation. Now look at this picture. What are electromagnetic radiation? At the very long wavelength, you have radio waves, and they are about a kilometer long. You can see about a kilometer long. And these wavelengths are given in nanometer. You know what a nanometer is? A billionth of a meter. As you come down to infrared, I told you what infrared are. Infrared are heat rays. And they are about 10 nanometers long. Now, come down, you have visible light, and look at the visible light. Visible light is made up of so many colors, and each color has a different wavelength. You see, each color has a different wavelength and frequency. And after, you got ultraviolet, X-rays, gamma rays. They are very short waves and very high energy waves. So the electromagnetic radiation, all this radiation is actually coming from the sun. When you heat this rod will emit all kinds of radiation. Alright? Now, visible light is a collection of over 3,000 waves, ranging from red at the long. You see, visible light is a collection of over 3,000 waves, ranging from red on the right end, at the long wavelength end, to violet at the short wavelength. So red is very long waves in the visible light, and violet are short waves in the visible light. Alright. Now, We will now look at electrical energy. Electrical energy. We had a glimpse at the radiant energy. We will have a look at it later on in some other lesson. But at the moment we will stop there and now look at electrical energy. A little while ago I told you how to produce electricity by turning a coil of wire, rotating a coil of wire in a magnetic field. In fact, any form of energy, there are many different types of energy that can be used to do this work. That means many forms of energy can be converted to electrical energy. Electrical energy is produced by turning huge turbines. So those coils of wire are not small like the one I showed you. They are very huge because we need to produce power at a very large scale. Huge turbines causing electric and magnetic fields to interact. So that is why we rotate a coil of wire in a magnetic field. It is the interaction between the electric field and the magnetic field that produces the electric current. Now, this is a picture of a turbine. You can see how it is constructed. It is constructed in such a way that steam injected onto this can rotate it. So this is a steam turbine. Now, in most commercial power plants, the turbines are turned by using heat generated by burning coal or oil. It is the pressure of the steam that rotates the turbines. Now, in most coal-fired power plants, chunks of coal are crushed into fine powder and are fed into a combustion unit. You know what a combustion unit is? A unit where coal will undergo chemical action with oxygen, releasing that locked up energy. That is the combustion unit. Then heat from the burning coal is used to generate steam that is used to spin one or more turbines to produce electricity. In a normal generating plant, there will be many of these turbines working at the same time. Now, here is a coal-powered generating station, and you can see the amount of coal that is used by one coal generating plant. Now, burning coal and oil releases carbon dioxide and other greenhouse gases to the atmosphere. I know I told you this once, but I keep on repeating it because that's something that we all must be conscious of. Now, what are some renewable sources of energy? Sources of energy that will not finish off, like the fossil fuels. You see, coal and oil will finish off. You cannot renew it. It takes millions and millions of years for a new batch to be produced. Well, we won't be there to see it. What are some of the renewable sources of energy? Well, renewable energy is electricity produced from sources that replenish themselves naturally. Can you tell me some of those replenishable energy sources? Well, this includes the wind energy, solar energy, landfill. You see, a lot of garbage that we actually bury in landfills are a very good source of energy. There are a lot of energy locked up in there. We can actually use those for producing cooking gas and electricity and so on. Landfill, agricultural waste, biomass. In fact, there are some parts in India where cooking gas for families are produced locally at home. You have 2 cows at home. The cow dung can actually produce cooking gas, methane. And what is left over is good manure for the farm. So if you go into village areas, you can see little cottage industries. It is not a big plant, but it is quite sufficient for the needs of a family. You see how you can save energy, money, and save our atmosphere, our environment by doing these kind of things. You can convert biomass into energy, and the heat from the earth, the inside of the earth is a big reservoir of heat. The internal temperature at the core is about 4,000 degrees Celsius. And go deeper into the mantle and into the core, you can see water boiled and stored in the form of very hot water or steam. There are lots of energy stored inside the earth. You can use that. So all these are renewable sources of energy. So they have less impact on the environment than traditional methods of electricity generation, which includes burning of fossil fuels and so on. Let's look at some renewable sources of energy. One is hydroelectric power. What is hydroelectric power? The power of water. If a river running between two hills, if you build a dam, you can collect all that water. And if you allow that water to run through a pipe way down into the valley, this water, you see that water at the top has a lot of potential energy. Is that right? That water running down to the valley will convert all that potential energy to kinetic energy. And if you now use a turbine there, that will turn the turbine, producing electricity. You see how power of water can be used to produce electricity. Turbines can also be turned using the potential energy of stored water. A dam is built to trap water, usually in a valley, because it is convenient to build the dam between two hills where there is an existing lake or river. Now look at the Hoover Dam. Got a great big dam, is that right? Now that collects millions and trillions of gallons of water, and now the potential energy of that water is a tremendous amount of energy. If you now let that water flow down, you can actually turn hundreds of turbines producing large amounts of electricity. Now here I have a schematic diagram of it. If this is the reservoir of water, look at the way water is run down the pipe. When the water runs down, all this potential energy is changed to kinetic energy, and now it turns the turbine. There you have the turbine. The turbine is made to turn due to that energy which produces electricity, and that electricity is brought up and distributed to many regions. Well, that is a hydroelectric plant, a typical hydroelectric plant. As water runs down the pipe, it gains kinetic energy which turns the water turbines, producing electricity. Now such a power plant is called a hydroelectric power plant. Now this is another diagram there. This is the reservoir. You let the water flow, and here's a turbine that rotates the turbine, producing electricity. And here I have the picture of a water turbine. You let water flow in with a large speed. You can see that's the coil. Big coils are wound inside, and this coil is rotating inside a magnetic field, producing electricity. Well, another renewable source of energy is the solar energy. There are homes around in Florida that uses only solar energy. You can produce electricity from solar energy and run your entire home by solar energy only. So solar thermal electric systems meet the need of over 350,000 people in California and Miami. Now this is a typical solar collector, panels that will absorb heat from the sun and that energy can then be used to produce electricity. The one in California is a 10 megawatt prototype. What's a megawatt? I told you what a megawatt is. A megawatt is 1,000,000 watt. In other words, the power station will generate 1,000,000 joules of energy in 1 second. That is a megawatt power plant. So this is a megawatt prototype commercial plant which stores sun's energy in molten salt. So the energy from the sun is used to heat up the salt solution, and the heat goes up to 1,000 degrees there, which then allows to generate power day and night. Because that heat can be stored, you can use that heat not only when the sun comes on, but also when the sun is not on. Another kind of solar collector, if you notice, all these parabolic mirrors will reflect heat onto a central axis. And if there is a pipe running water there, that water will boil with that heat. You can actually collect a tremendous amount of heat that way and boil water. Parabolic troughs consist of curved mirrors. These are the curved mirrors that focus the sun's energy on a pipe. The pipe is running down here. So all the energy is focused by all the mirrors to the same place. And that means the water can be heated to a very high temperature or even boiled. Other type of renewable energy is geothermal energy. What is geothermal? Is the energy stored inside the earth. Energy stored inside the earth is geothermal energy. Earth is a vast reservoir of energy. It contains very large amounts of energy. Now, geothermal means heat from the earth. The heat that flows from the earth's hot interior due to crustal plate movement. Well, if anybody did part 1 of this course, we have a good description of what is called plate tectonics. All the movements of the earth's crustal plates that causes all kinds of changes on the surface of the earth, including diastrophism, volcanism, and earthquakes. Now, all these processes are in the earth's interior. Now, and all these traps actually a lot of heat in the earth. So the heat that flows from the earth's hot interior due to the crustal plate movements. When the earth's crustal plates move and they collide and crack, there will be space through which the molten rock can come up. And the heat from inside the earth is actually brought out. There are many places on the surface of the earth where the heat from interior of the earth is brought to the surface. Well, volcanoes are one great example. Now here is an example of the crustal movement as a result of the faults in the plates, places where there are breakages, the molten lava will come up, and you can see the formation of volcanoes is the result of that. And all these put together is what we call the plate tectonics. Now look at the heat that is coming from interior of the earth. Now this is a place that actually exists on the surface of the earth, where water, warm water and steam keeps coming up from interior. Now if you can trap that energy, you can produce electricity from there. Geothermal is an endless resource of renewable energy. So rainwater can seep down, fall. So as rainwater flows down through cracks and crevices, they go to the interior, gets boiled and becomes steam, and that steam is what you see is coming out. Now water goes down into the earth's interior and brings up the heat from interior. That's a free supply of heat that actually we can use to generate electricity. And look at some of these pictures at places where the heat from inside the earth. This is a hot spring, and you can see heat from the sun, heat from inside the earth is actually bubbling up. You can see bubbles coming up. They're very hot. So there are lots of supplies of energy from inside the earth that is available for us to make use of in producing electricity. When hot water and steam reach the surface, they can form fumaroles, that's a fumarole, hot springs, that's a hot spring, mud pods, and other interesting phenomena. All these are found at many places on the surface of the earth. And you have wind energy, and there are many places wind energy is harnessed to produce electricity. Wind is the fastest growing source of electricity in the world. Across Canada and the United States, electricity generated from wind is powering homes and businesses, which is a clean, reliable, and efficient source of energy. So we must make use of more and more of these resources. And I have a picture of various states in America that uses wind energy. The total installed wind capacity in the United States is 6,740 megawatt. And you can see California alone has 2,096 megawatt produced from wind energy. And unfortunately, Florida, which is supposed to be the sunshine state, we have no wind energy. Is that right? We have beautiful wind. We can make use of that wind if we want, but nobody has tried so far. I think people should come forward and develop wind energy all over. That is a cheap and efficient way to produce better and renewable energy. Now, here I have some pictures of wind farms. Now, this is a US wind farm. And another kind of energy is nuclear energy. Now, nuclear energy has been in the 60s and 70s. Many countries went ahead and built a number of nuclear reactors which can then power plant to produce electricity. But if you remember the 3 Mile Island accident and the Chernobyl accident in Russia, now they actually put a dam on the nuclear power generation. Now, safety is the first concern. Now, that is the main concern. Can we build nuclear reactors that are safe enough? If a nuclear reactor explodes or it melts down, it is almost like an atom bomb, which will disrupt the lives of millions of people and cause death and destruction. So, if we cannot build secure and safe nuclear reactors, then we shouldn't. Is that right? But now there is a movement all over the world, and there is now hope that we will be able to build better and safe nuclear reactors, and that will be the best way to power our next generation. In fact, most of the electricity used in France is actually produced from nuclear reactors. Now, in the formation of matter, particles of matter are brought together doing work on them. So when matter is formed, particles are brought together doing work. That means if we can separate them, that energy can be used. A nucleus, if it is split, the energy can be released from them. So this energy can be released by breaking matter into constituent particles. And that is what is done in nuclear fission. when nucleus of materials like uranium and plutonium are broken into constituent particles, large amounts of energy are released. Now, this energy, if tapped properly, that's the key word there, if tapped properly, can be used to produce electricity in a nuclear reactor. If used improperly, it will be like making a bomb, because it is producing a lot of harmful radiations that can affect lives adversely for several hundred years. Now here we have a nuclear reactor, the picture of a nuclear reactor, and the energy from that is used in constructing electricity. Now here I have a schematic diagram of a nuclear power plant. Now this is the main nuclear reactor. I don't know, a part of this may be cut off in the picture, but this is the nuclear fuel, the uranium nuclear fuel rods, and you can see inside heavy water. And when nuclear fission occurs, the energy that is released during fission will heat up. It will heat water, releasing great amount of steam at great pressure. You can see that steam can be regulated and can be led into. Here we have a series of steam turbines which will then generate electricity, and that electricity can then be used. This water can be recycled, cooled and pumped back in there. In a nutshell, that is a nuclear reactor. But the problem is how to build a reactor strong enough and safe enough to contain all the nuclear materials which are very highly radioactive. If the radiations come out, that can be deadly for thousands of people living around. Alright, we can now actually simulate it on several sequences and see what can go wrong when the temperature is not controlled. It can burst. Now I'm going to work sequence 1, sequence 2 and so on, and see what happens when the temperature goes out of control. Now you can see here the temperature is building up in there. Alright, it's building up here. Oh boy, the turbines that got completely busted. Alright, let's stop that and try sequence 2. There you can see heat generated, steam generating 617 megawatt of electricity, and the pressure is building up. You can see the fuel, the water is getting finished now, it's going to explode. Look at that, the fuel is melting. This is a meltdown, the whole thing is going to explode. Now this is what happened in Chernobyl. This is a complete meltdown. The reactor is now more or less like a bomb. You see, it has now all these areas that contaminated, the radiations are all over, hundreds of thousands of square miles are now absolutely not good for human population. Well, that is one way. Alright, let's have a look at another one, as sequence 3. What can happen? Again, you can see the temperature increases, the pressure increases, you can see the electricity produced. What happens? The pressure inside got so high, it got busted. So what you notice here is that you need great safety precautions. And I think we have now learned how to make a nuclear reactor safe. Now, all this needs to be taken into consideration when you opt for nuclear reactors. And I think in the United States, at least I know one company, one power company, has signed up to manufacture nuclear reactors. Alright, so let's move on. Now, uranium is a very heavy metal. Uranium is a fuel used in nuclear reactors. Now, you can see the yellow metal. You probably remember President Bush's speech way back in 2002, is that right, in the State of the Union address about the yellow cake from what country? Chad, Niger. Yes, about Saddam Hussein buying the yellow cake from Niger, an African country, well, which proved to be a wrong information. Well, this is the yellow cake, the uranium, which is fuel for nuclear reactors. So like coal, oil and natural gas, uranium is an energy resource which must be processed through a series of steps to produce efficient fuel for the use of generating electricity. Well, let's now talk about another form of renewable energy. That is the energy that can be tapped from tides. Tidal energy. What is tidal energy? These work rather like hydroelectric scheme. So tidal energy is more or less like hydroelectric energy, where the power of water used to turn turbine. But the dam that is built to use the power of tides has to be very, very big and long, because in the sea you cannot get hills narrowed down so that you can build a small dam. If you want to use up the power of the big tides that come in, you have to build very long barge-like great dams. Now look at a great big dam that is used to harness the power of tides. Now a huge dam called the barrage, this is called a barrage, is built across a river estuary. That is the best place because that's the shortest to where we can build this. Now when tides goes in and out, you can see when tides come in, you can allow a decent enough area where the water will flow in, and you can build a turbine there. So when the tides come in, you generate electricity, and when it goes out here, again you can have electricity. So that when the tides come in, the flow will turn the turbine. When the tides go out, the flow will again generate electricity. A very, very efficient way to produce electricity. So the tide coming in, this is the sea, the tide is coming into the estuary, the turbine turns, generating electricity. And now the tide is going out into the sea, electricity is generated again. Both those times. But the snag here is that only during twice a day this happens, is that right? So you cannot have a continuous generation of electricity. The ebb and flow of the tides can be used to turn turbines. A major drawback of tidal power stations is that they can only generate when the tide is flowing in or out. That is about 10 hours a day. But, well, 10 hours a day of producing electricity is okay, because we are getting that power free. Is that right? We are not using coal, we are not using nuclear fuel, we are not paying for anything, we are not polluting our environment. You get it free. So 10 hours of electricity produced by using the power of tides is pretty good, I think, and we must do more of that. Talks exhaustively on the concept of energy. Well, at least in a course like this, we cannot do more than this. And it is a very important concept. And I hope you have some idea about the energy our energy needs, the energy available in the universe, and most of all, as I told you, why it is important to conserve and use the energy we have in a responsible way. And as science students, you and I have the responsibility to educate the rest of the population so that the people understand that there is a value in being responsible. Is that right? Responsible citizens of a country, responsible citizens of the world, so that we leave the world as at least as we found it, so that the later generations will enjoy it as much as we do. Okay, in our next lesson, I will touch on one important type of energy, that is heat energy. And that is going to be our theme for lesson 3 of this unit. This is the unit on energy. All right, I will see you for that lesson a little later.